Dear guests, welcome to day 3 of this Pepperl+Fuchs online summit. 3 days, 3 topics and 3 different formats. We have keynotes, we have presentations and we have our panel discussions with experts to discuss the topics in detail. My name is Oliver Sequenz and I'm your host for this extraordinary event. Well, we decided this time to make it all digital, of course, due to the COVID-19 pandemic in Germany and all over the world. Our topic today is a technology which is older than mankind. And some animals would now go like, oh, come on, that's old hat. We use this for millions of years for orientation and communication. But the thing is, we wouldn't hear it. Ultrasonic. Well, of course, we use it every day, for example, in cars, for parking, for distance measurement. But in an industrial environment, the challenges and requirements are much bigger. And here comes Pepperl+Fuchs into play with wireless and state-of-the-art ultrasonic sensors. And we show you how you can benefit from them. Please enjoy the keynote from Joachim Schulderer, Head of Innovation Unit Ultrasonic Sensors.
Thank you for the introduction, Oliver. And hello and welcome to all of you. Thanks for joining us and showing your interest. I would like to draw your attention in the next 10 minutes to the topic how the next level of ultrasonic technology is connected to the digital transformation and how we do provide additional customer benefits with our smart ultrasonic solutions. This digital transformation means mobile technologies, robotics, cobotics, IoT, big data, cloud computing, and cybersecurity, where mobile technologies is strongly pushing the technical development regarding computing power, system-on-chip, miniaturization, low power consumption and battery technologies. And where robotics cooperating with human beings, cobotics called, means autonomous or semi-autonomous machines are working together in environments with people in the same time or even interacting with them. Such machines need to fulfill safety requirements, which are standardized as functional safety levels or performance levels. These are core technologies for our sensor innovations. These technologies allow the interaction of additional and complex functionality and the local sensor, which means decentralization. What requires HMIs for ease of use, interfaces for local point-to-point interaction, displays, mobiles, Bluetooth, near-field communication, etc., and for remote interaction, IO-Link, LoRaWAN, or IP protocols, for example, for the purpose of commissioning, monitoring, operation, and service. Smart sensors, therefore, meanwhile, integrate several communication systems at a time, and those with increasing bandwidth. So this is the aspect of connectivity. And of course, this needs to be done in a secure way. So secured communication means cybersecurity. This seems to be nothing new so far. Yes, this is true. All of these words and topics we know since years. And know is also the differences. The available computational power is still increasing with an amazing speed, and more open standardization is available. So this is pushing the innovation all the time. With other words, digital transformation meets IoT, or at Pepperl+Fuchs, Sensoric 4.0. So this allows to develop robust and smart ultrasonic sensors. To mention some examples, we provide an ATGS called sensor with integrated local complex functionality and smart IO-Link profile with a wide operation range, which can be configured with diagnostic functionality, with robustness functionality, and status functions, for example. So this is a smart product. With Wilson, we provide also an autonomously operating device, ultrasonic sensor, which is battery powered and wireless connected, so not wired in any way. So this can be used decentral and therefore opens access to up to now not available assets and infrastructure components to integrate them in automation processes. And last but not least, ultrasonic safety. Our fascinating ultrasonic solution for safety level PLD category 3 applications to protect people in mobile equipment, semi and autonomous mobile vehicles, cooperating robots and some more. With double channel and specific elliptic ultrasonic sensors and some other keen features. This means smart and safe. Of course, all of these sensors are of high robustness for usage in harsh environments, what is typical for our products. So far my part, I hope I was able to illuminate the context between digital transformation and the next level of Pepperl+Fuchs ultrasonic technology. In the following, Till Hoffmeier will provide more insights into smart and autonomic, and smart and safe products. In the subsequent panel discussion, we will address some of these IoT aspects under the headline Evolution from Transmitter to Smart Sensor, with our guest Dominik Fischer from Digitalagentur Heidelberg and our colleagues Sonja Armbruster, Wolfgang Weber and Michael Botzek. I would like to thank them in advance. I also thank you for listening, and I'm sure you will get more and useful information in the subsequent parts. Thank you, and I hand over back to you, Oliver.
So thanks, Joachim Schullerer. And now we want to go more into detail, and therefore please welcome Till Hoffmeier, and he will show you 3 technical highlights and use cases.
Thank you, Oliver. Hello, my name is Till Hoffmeier, Product Manager Ultrasonics at Pepperl+Fuchs, and today I have 3 highlights of ultrasonic technology that I'd like to show to you. Smart, safe, and autonomous. Those are going to be the 3 topics we'll cover today, and we'll jump right in to smart. What you see here is a sensor that you also can see on the table with just 18 millimeters in diameter. And it packs a whole lot of functions and features on a big punch. How does ultrasonic technology work? Well, mainly we emit sound waves in the ultrasound spectrum that we cannot hear as a human. And we measure the time it takes for that wave to get to a target, to an object, gets reflected and then comes back to our sensor, gets measured, and we can calculate the distance out of that. For that, we need, besides the time, also the speed of sound, which itself is dependent on the temperature. So every ultrasonic sensor has a temperature sensor built inside, so we can measure accurately our distance. 2 main reflection modes occur. The first is on a smooth surface, where we get lots of reflection back if the surface is perpendicular to our ultrasonic sensor, and where sound gets reflected away once it starts to get inclined a little bit. The more it's inclined, the more gets reflected back. So the idea here would be, how can I maximize the sound that gets reflected back? We'll see that in a short bit. And a second application or second occurrence would be a rough surface where the sound gets scattered once it touches the object, the target, and we get reflections back that are weaker because the sound gets scattered. And so we can measure here even if we have an inclination of the object. One application where we have a smooth surface most of the times are if you want to measure the filling level in a tank. Here, one of the main hindrance or the main challenges is if you want to mount the sensor on the outside, so we can protect what's inside the tank from any outside influence. Often, the ultrasonic sensor gets mounted in an extra tube that then looks through a hole in the tank inside to measure the filling level. If we use a standard sound cone, we will see what's around the hole. So in this case, around 9 centimeters. If you want to look through, We need to adjust the sound beam width so that it actually gets through that hole and we can measure our tank level with a better precision and reliably, of course. Now, in a short video sequence, we'll see how that process works in practice. We want to measure the filling level using ultrasonic technology. That is perfect for that purpose. We have a smooth surface, and in order to protect what's inside the tank from any outside influence, the sensor is mounted in a tube on top, and the sound wave has to travel through a hole. Currently, we measure the first echo, which is the opening or what's around it. And if you want to accurately measure the filling level in the tank, we can reduce the sound cone by up to 50% without losing range. You can even get down to 10%. The second application where we can put our smart in ultrasonics to use is when we have fortifying structures inside a tank or in any application when something protrudes into the area of our sound cone. In this application, we see a metal beam that gives us a permanent echo in our application. And via software, we can use the target suppression mode, where we'll suppress any echoes that come at precisely that distance and with the amplitude of our metal beam. And every other echo will still get counted, measured, and be included in the distance value that is given back from the sensor. So if the filling level of the tank rises, we get continuous results from low to up, and only that precise echo that we suppressed will be excluded from any echo measurements. The third feature that is really smart for ultrasonics is that our ultrasonic sensors can communicate among themselves very easily. You just have to link them via wire in order to decide who is going to send and receive. Why is that of use? If you mount more than one sensor next to each other, how would one sensor know is that ultrasonic wave that I'm receiving actually from me or from the other sensor? So if you have many sensors mounted together and you want precisely to measure only what is in front of that sensor, we have one mode called multiplex mode, where one sensor is sending, receiving, and then giving information to the next one. Okay, I'm finished. Now you can send and receive, and up to the third one. That allows us to have independent measurements for every line of sensor without interference, so you can mount them closely together. The second mode of interest would be what we call common mode, where all three sensors send and receive at the same time. That feature is really interesting if you want to survey a whole area and you even want to get the cross echoes back, so you can really reliably see anything that is in the area of interest. And they all send and receive at the same time and evaluate the echoes and give you a presence detection or distance measured from these echo waves reflected. Now we're going to see a short video sequence of the multiplex mode working in practice. Okay, we're in a bottling plant, and our robot here is taking the bottles out of the supply line and putting them into crates. The sensors are checking whether there are enough bottles in their lane for the robot to pick them up. They're mounted very closely together so that they can reliably measure only their lane. They are configured in multiplex mode, just by linking the sensors together. What's happening here is that one of the lane gets stuck, and in multiplex mode here, of course, very slowly, they check whether they have enough bottles in their lane. That one in the middle is stuck. Now the bottle gets to the front. We, again, in multiplex mode, check, okay, do we have enough bottles? And once every lane is complete, the robot takes the bottles and puts them in the crate. We have lots of smart features that allow us to seamlessly integrate in applications that are existing, to configure our sensor to the needs of the application. And you have a very smart and easy way to do that by using the IO-Link communication protocol, where you can easily configure your target suppression mode, where you can easily configure your sound beam width, and all the other possibilities that ultrasonic allows you. And additionally, you get the temperature value and the operating time as well, besides the distance. And all that can be then used in your machine via an IO-Link master, or you can use the IO-Link master USB so you can link it and test it on your PC. Safe. Second topic we're going to talk about today. Ultrasonic is not only smart, but it can also work in safe applications. Why is ultrasonic ideal for safety applications? Of course, first, you need to be certified. We have ultrasonic technology certified at performance level D, category 3, and we have the possibility to use an elliptic sound cone, which allows us to cover more area than with current LiDAR or other optical scanners, which only have a plane that they can survey. We can easily configure our protection and warning zone so that we can decide when the machine, application, mobile equipment has to stop and when we want to issue a warning. We're immune to dust and fog, and we are also insensitive to light. So all the applications, outdoor, rain, dust, that hinder other safety applications are no problem for ultrasonic. We also have a high IP rating, and as you can see in the next slide, we have the possibility to survey areas from 1 centimeter to 250 centimeters with a resolution of 1 centimeter. Both ultrasonic heads can work independently, one from each other. They have 2 independent microcontrollers that are programmed differently, and one microcontroller is checking the sensor of the other microcontroller and is checking the validity and integrity of the signal received. So we always can be sure that the measurements taken by the ultrasonic sensors are reliable and safe. Every ultrasonic sensor has 2 safe OSSD outputs, and we have a special software function that allows you to suppress any other ultrasonic wave that is coming in from another safety ultrasonic application. That would be the case if 2 robots meet themselves, both equipped with ultrasonic safety sensors, and they can reliably suppress the signal, the ultrasonic wave from the other robot without getting confused. Because otherwise, when you receive an ultrasonic wave with a distance that could be then in the protection zone, it will stop. So you can reliably control and operate many applications using ultrasonic safety technology next to each other. One example would be a robot working at a tooling machine. Tooling machine often means there can be some rough environments as dust and fog or a little bit of dirt that happens to be there. And that robot normally could be used to put metal parts inside the machine so they can be tooled or milled. And if a human operator would want to step in without any safety ultrasonic features, there would be a cage. You would need to open the cage, shut the whole machine down. And here you can reliably operate a robot arm with ultrasonic field protection, and only if the human would want to step in, you know, okay, now there is a human presence, we want to protect the human from the machine would shut down until the human leaves that area and then continue operating. And that allows for maintenance or operation checks of humans next to a machine that is operated with a robot. Second application we have are autonomous vehicles. Example here would be in material handling that are moving around, and an example would be to mount the ultrasonic transducers in front in the forks, and so you can reliably see what's happening in front of the fork. Is there an obstacle? We have an elliptic sound cone, so we can cover a 3-dimensional area and see what's actually happening in front. We have a protection field, we have a warning field that we can configure via software, and that can then be used to automate these vehicles, even in an environment where humans are present. Autonomous, our third subject of the day, and we'll see how ultrasonic fits into that and what it actually means. Autonomous is a sensor I need if I want to work in an IoT application, or if I want that sensor to function there. What is IoT for us, or for that sensor? Data access everywhere and every time. We have a sensor that is autonomous, so it works independently from a machine, independently from cables, independently from a permanent power source, but we can still access the data it collects every time and everywhere. We have on-demand information that we can use, so it just only sends when we want it to, or when we configure it to do so. We have less reaction time, because we don't need to drive anywhere and get the data manually out of the sensor by plugging a cable or something. We have a higher system resilience, because we don't need to make it accessible easily. It can be mounted anywhere. And it can be self-regulated. Once there's data or an information that comes from that sensor, it can be used somewhere else without any human touching. And last but not least, process optimization. We need less resources to check our devices, our components. We need less time to do so, and we can save resources, money, time, and are more productive. One use case for IoT sensors would be checking filling levels all over town. An example could be now in winter time, where we need salt at almost every place in case there's snow or ice to get the roads and spots and pavements clean or safe again. We have different depots at almost every tram station here in Mannheim, but they're very small, and the filling level can only be checked manually because there's no other way than opening the hatch, looking inside, and see how much is left. If you could use an IoT sensor here that would be mounted at every one of these depots, we could reliably check the filling level, get that filling level back to a backend somewhere in the cloud, and only if a filling level reaches critical level, you can go to that depot and fill that one up. So in case there is ice or snow situation, you can be sure that there is enough material to cover what you need on site. What do you need for that? You need a sensor checking the filling level. You need a battery so that that sensor has power. You need a way to communicate, a wireless way, and you need to put everything inside a housing so it is protected from the environment and can be put easily in place and can be configured without any problems. One example would be our Wilson from Pepperl+Fuchs. It's a box that contains everything you would need for that application. We have the possibility to locate that sensor via GPS built inside. We can check the filling level of our depot of salt. We always have the actual temperature because we need that one to measure ultrasonic distance accurately. We have the battery status, so we can see, okay, is either the filling level critical or the battery status of our Wilson. And we have that one in an IP67 protected housing. So it is really immune to any environmental issues and challenges that might be at that place. And to configure it on site, when you put it in use, you can use the Wilson application that communicates via Bluetooth with the Wilson sensor, so you can register it on a standard LoRa WAN network to any LoRa gateway. Any LoRa gateway can be used. It is currently the market leader and is very low power, very efficient, and has a long range. So you're not limited to any backend. You're not tying yourself to a customer. You can use Wilson in every LoRa WAN. And Mannheim and Heidelberg are two cities that built up LoRa WAN infrastructure, and the next LoRa WAN gateway in range, you can register your Wilson sensor to that one. Use cases for IoT sensors or for Wilson, I just gave you a small example. Device and component management, whenever you have devices and components scattered around a zone that takes long time to reach or is difficult to reach, with the built-in GPS, you know where they are, you know their condition, and you can dispatch aid or maintenance and exchange on demand. You can check for availability and reliability of your IoT sensors by getting signals back. Is it still working properly? Did something change? Did I have some alarms while I was away? I can log them all online and use them later for statistics, to have deviations over my sensors, to have deviations over time. And so I can really check for every application, where can I optimize? Why did something happen? How did it happen? And I have all that information in my cloud, in my software, and I don't need to touch a finger for that. Now, we're going to see two sample applications of Wilson where you can use it in the real world.
IoT sensors help us to facilitate our daily work and to obtain valuable information about our environment in a timely manner. The wireless sensor Wilson sonic level transmits not only the level data measured by the ultrasonic sensor, but also the current geoposition and other information such as temperature values and battery condition. Its standardized LoRaWAN interface enables the sensor to transmit the relevant data over many kilometers. With these features, the Wilson sonic level can be used for flood protection. For this purpose, the sensor is mounted under a bridge, for example. With the integrated ultrasonic sensor, it continuously measures the current water level and sends the measured data to the LoRaWAN network at regular intervals. From there, the data is forwarded to an application server, which converts it into water level information and displays it. This regular control of the water level allows forecast for the near future and leads to better protection against flooding. The Wilson sonic level also provides a valuable contribution to the efficient control of agricultural operations with its intelligent level management. Agricultural businesses are suppliers of both food and energy, and therefore an important source for our society. The Wilson sonic level helps farmers to remotely monitor the fill level in distributed feed silos or the pit of a biogas plant. The sensor measures the fill level by means of ultrasonic pulses and sends the measured values at regular intervals to the farmer's private LoRa network. From there, he can also monitor the status of his feed silos with the help of a mobile device. The system informs the farmer at which location the filling level of feed becomes low. This enables him to trigger a reorder in time. Such IoT systems relieve the farmer of inspection rounds and create space for important tasks in his efficient operation.
Smart, safe, and autonomous. Those were the three highlights of ultrasonic technology, totally different applications, totally different use cases, and it all can be done with ultrasonic. Really, ultrasonic next level. But of course, we don't only have these three use cases with these three sample products. We have ultrasonic, a whole portfolio with different ranges, different configurations, different housings. So you will find the perfect ultrasonic sensor for your application. Thank you very much for your attention. It was a pleasure showing you these highlights today. And I'm going to hand over to Oliver to the panel discussion.
Thanks, Till, and welcome, dear guests, to our panel discussion. Yeah, now we want to go into detail and have a closer look at ultrasonic and its use cases and the possibilities. And as I said before, due to the corona pandemic in Germany and all over the world, we decided to make this virtual online summit, and we meet in this virtual room for our panel discussions. But you have the opportunity to ask questions whenever you like. Just use our live chat option and our experts will answer your questions. So let me just give a brief overview who's joining this panel discussion. We have Sonja Armbruster, hello. We have Michael Botzek, we have Dominik Fischer and Wolfgang Weber. Maybe just give us a short introduction of yourself, and we start with Sonja.
Thank you, Oliver. Also, very warm welcome from my side. My name is Sonja Armbruster, and I'm a product manager for industrial communication at Pepperl+Fuchs. We're a central development team within Pepperl+Fuchs, developing interfaces for all our sensors and gateways, which our customers or users at the end will use to connect the devices to different gateways or other infrastructure components.
Thanks, Sonja. And we proceed with Michael.
Yeah, hello together. My name is Michael Botzek, and I'm working as business development manager right from the ultrasonic innovation unit. And as this, I guided our new development of IoT sensor right from the ultrasound innovation unit, which is called the Wilson product. And now I'm very interested how this brand new product will go to the market and hopefully also enjoy our customers.
Thanks, Michael. Okay, it's not Michael, it's Michael. Then we proceed with Dominik Fischer. I guess it's Dominik Fischer.
Hello, my name is Dominik Fischer. I am from Heidelberg, from the digital agency Heidelberg. And we are working on several IoT projects as well with the Pepperl+Fuchs product Wilson. And I think we are one of the first customers.
Thanks, Dominik. Wolfgang, please.
Yeah, last but not least, I'm Global Industry Manager here in the headquarters from Pepperl+Fuchs in Mannheim. Well, we are dealing generally more with strategic questions, but if we are entering a new market, for instance, like what we are talking about in a few minutes, which is not really in the focus so far of Pepperl+Fuchs, that's a typical thing where I get involved.
Yeah, it's not that typical, and this is why we're talking about this today. But first, let's maybe just start with a little history. When we have a look at the first proximity switch of Pepperl+Fuchs, it was long time ago, ages, so to say. What was the development since then, Sonja?
Yeah, when we have a closer look at the evolution of our sensors or even actuators, we will recognize that sensors and actuators getting more and more intelligent. So what is the reason for this? I think in the year 2000 or even a bit before, microcontrollers went inside these devices. And so from this days on, we had the possibility to not only get measurement signals or switching signals from the sensor, like digital and analog signals, we were able to put communication interfaces inside these devices. And so today we talk about interfaces which are standardized, like IO-Link or industrial Ethernet interfaces, or even a CAN product as possible. So that means today we're able to get more data from a sensor, which helps and enable us to open the world to Industry 4.0.
You just mentioned IO-Link, and we had this before today. What are the advantages for the user?
Yes, so IO-Link is a really smart communication profile. It's a bidirectional point-to-point communication. And what does it mean? In the past, we got the signal from a sensor, and that was it. So, and there was no chance to do something like parameterization or to do identification or even diagnosis was not possible. And the reason why we have this chance today is because we have this bidirectional communication. That means we can talk or take informations out of the sensor by just asking for the informations from a master or from a PLC through the sensor. So we opened up the way not only from a sensor up to a PLC, also from a PLC down to a sensor. And this, there was IO-Link is IO-Link the main technology used today for our devices.
Almost incredible what's possible. So thinking of use cases, Michael, well, sensors can be used to measure data, to provide data, and that in a extremely, let's say, different context than some might have thought.
Yeah, well, that's right. So in the past, we used to use the sensors as the electronic components for machines and plants, and the sensors are the eyes and ears for the machines and for the plants. And well, they're getting more and more intelligence. They're getting more and more smart, as Sonja already mentioned. And with those new interfaces, communication protocols, we are able to transfer not only data, but also information right from the sensor to a PLC. And if we think about this picture, eyes and ears of a machine, and if we transfer all these information, also the status data, for example, to a central point on an IT platform, for example, then we come to the picture of the Internet of Things, the IoT. And well, with this, sensors are becoming more and more eyes and ears of the internet. So very important, very interesting use case.
It's a nice image you just created. So Heidelberg now is provided by Pepperl+Fuchs with many eyes and ears. So Dominik and Wolfgang, give us a little picture about what happened in the last 2-3 years.
Yeah, if I should start, actually, we had a meeting in Heidelberg 2017, not only with a digital agency of Heidelberg, but also with SAP, with a high-positioned manager, I have to say, on the table. And we started this discussion around the topic smart city. Yeah. And the difference to IO-Link and what Sonja and Michael said before, we here now talking about a wireless technology, yeah, because we wanted to equip, and Dominic will explain that later a little bit more precisely. We wanted to equip containers with autonomous sensors. That means sensors which are independent from a plug. They have their own power supply, and they are communicating wireless. Yeah, and that was really our entrance into this technology.
Yeah, back in 2017, it was a great match with Pepperl+Fuchs because Heidelberg just started to build up their IoT network in Heidelberg for the city and for the electricity company in Heidelberg. So it was a great match for the use case smart waste with the glass containers.
It's not only smart waste, what else?
Yeah, it's also about, in our project, Winter Smart. And for the road conditions, we're using the salt, of course. And there we have silos, which are now monitored by the Pepperl+Fuchs sensors. And then we have a new use case. Just a few weeks ago, we started with it. It's the power plant with wood pellets. And there we're looking also into the silos and using the sensors to measure the fill-up level.
We'll have a closer look at these projects later, but let's have a look now at the sensors. These are the Wilson sensors. So why are they used?
Yeah, if I may answer this question. As a matter of fact, in 2017, when we had this discussion, the Wilson product was not existing. The surprise at that point of time was that Heidelberg explained they are building a LoRa network in Heidelberg. So this is the wireless technology which gave us the starting point to develop this product, what we call Wilson now. Wilson is a sensor, and our first sensor with a LoRa interface, a wireless interface, low power wireless interface, which is transmitting the data to this IoT platform. And that was really the starting point for this development.
Because for us, it was very important to have a sensor with low power consumption, and which runs on also with LoRaWAN, because we just built up the IoT network in Heidelberg.
So, as you just said, the Wilson sensors weren't invented yet. Why did you choose then, or what was the development of the Wilson sensor with LoRaWAN?
We're choosing LoRaWAN because this is, in comparison to 5G, for example, this is a very suitable radio or wireless connectivity technology for sensors we're providing with, like Wilson, for those kind of applications. So 5G, for example, as a mobile communication standard is very good in bandwidth, for example, which is useful for consumers to upload videos, for example. And it's also good for industrial purposes with a very, very low latency, so that we are able to control vehicles, for example, remote control vehicles. But with those kind of sensors we are addressing with our Wilson product, we need technology which is very low in energy consumption. And for those purposes, there are different technologies available on the market, which are the so-called low power WAN technologies. And one of these technologies is LoRaWAN, which is meaning a long range, wide area network. And it's working on very, very low power consumption to transmit all the data to the internet.
Maybe in addition to this, we have also a really good building penetration with LoRaWAN. So for example, in the power plant with the wood pellets, it's no problem to get into the building.
What about the area of LoRaWAN? Is it available everywhere?
In Heidelberg, yes, we have now 13 gateways, which are on the high points in Heidelberg. And on street, we have a really good penetration. Maybe, in some big buildings, it's hard to get it. Yeah.
Maybe I can add something to Dominic. So, the distance we are able to reach with LoRa is about 1 to 3 kilometers in the urban areas, and it's 10 to 20 kilometers in the more rural areas. So it is quite a long distance to overcome with those sensor data.
Tough to imagine that it's just a little sensor and that it has this huge range to cover.
Right, yeah.
Well, as you just spoke about the 5G technology, well, okay, in this case, it wasn't necessary, but which role does it play in the further development of sensor technology?
Yeah, maybe if I may answer the question. That's not an easy one. First of all, we have to say we clearly must differentiate between these high performance networks like 5G, where a huge amount of data in a very short time must be transmitted. A very popular use case will be autonomous driving, for instance, in future. While here, in context with Wilson, with low power WAN, we are completely on the opposite side. Yes, we have very little data, only a few bytes. It's almost nothing. And we are transmitting maybe 3 times a day or 5 times a day. So these are two completely different technologies. And also, LoRaWAN is operating on a free frequency. Everybody can install a LoRa network, like Heidelberg did, like many other cities also do it, like companies doing it on their own premises, while 5G is in the domain of a big telecom company, like Telecom or Vodafone and so on. So we have to differentiate that we are here in really two different worlds, and it depends on the use case. Yeah, if you have a use case where latency and data rates are of no importance, then LoRaWAN is the solution. Yeah, if we need to transfer a lot of data in a very short time, when we must go to 4G or to 5G.
Yeah, maybe in addition to this, we only use LoRaWAN for non-critical use cases. So it's clear that in LoRaWAN, we also have the problem that 1 or 2 packages a day can be ripped out. So yeah, we just use it for soft use cases.
What are soft case?
Yeah, for example, the smart waste. So it's no problem if we lose a package from a glass container, because the next package is coming 4 hours later.
How about the implementation? Well, it sounds like pretty easy. I mean, you have the technology, you have the sensor. It was developed for that. But how did the implementation went?
Yeah, it was quite easy. The sensor is pretty small, and it's easy to install. It's just 2 screws. And then we set up the algorithm on the sensor, and then we connected it to our IoT platform.
Maybe to add something to this LoRa topic and integration topic. So LoRaWAN is from a different point of view very interesting for customers. As Wolfgang already told us that it is working on free frequencies, but it's also maintaining, developing, and marketing by a big community of more than 500 companies, and they perform and provide this as an open source standard to the world. And so there are some very important advantages for the customer. On one hand, with this open source idea, there are many components, many products, LoRaWAN products, in a very short period of time, on the market. And on the other hand, this gives also the user of this technology a long-term security for their investments. If there is a big community providing this in an open source manner.
Mm-hmm. And yet now I have, I would say, a long-term experience. It's like 2 years already. What are your experiences with, for example, battery or the data transmission?
The battery life is quite good. So we are expecting still 3 or 4 years more with the same battery, and then we have to replace it. So we have really less, work to be done with the sensors. We just installed them, and then we have several years of automated services from the sensor.
Yeah, battery is really a challenge. I mean, everybody has a mobile device today, like a smartphone or something like that, but everybody knows that he has to recharge his device every second day or so. But here, the requirement is that these sensors, if you like to call them so, should be work 5-6 years without any maintenance. Yeah, we have no possibility to recharge. And we don't want to change the batteries because that is service time which nobody wants to pay for. And fortunately, the development of batteries, lithium-ion batteries especially, we know it from the electrical cars also, has gone far the last year. And this is also a very important point, that we can now build sensors which are really working for 5, 6 or even more years every day.
Mm-hmm. Well, battery, that's a very crucial point. You mentioned, Dominic, before the Smart Winter project, and I can imagine, since it's winter, the temperature, it might be freezing. Well, batteries don't like that. And what about the sensor? So what are your experiences in the Smart Winter project, and what are your goals?
Yeah, what was one of the concerns that we have, that the battery dies in the winter because of the low temperatures. But in fact, it was no problem, and we still have a lot of battery life in the sensors we just installed. So that's not a problem. And the target in the future will be that we have in total 8 silos in Heidelberg monitored by the sensors. And we have also some LoRaWAN environmental sensors, which is in addition to the winter services, to have more data about the environment, especially in local microclimate zones. Yeah.
Maybe I can add something of the challenges we had here, because in opposite maybe to the glass containers or so on, we want to clearly identify when the silos gets empty, not so much if they are full. Yeah, that's not the critical point. And ultrasound is a distance measuring technology, yeah? But here in this case, actually the customer wants to have volume information. And that means we had to work on special algorithms, dealing number one with the special cone form of the salt, which is forming when it's getting empty, plus the volume, the size of the container. And we putting these data together in the sensor to deliver to the customer not only a distance information, but really a volume value. So we can say it's still 20% inside or 15% or whatever, because that is actually what the customer wants to know. And this is something we are doing in the sensor. So that means we have a lot of computing power already in the edge device, and we must not take loads and airtime via the LoRaWAN to transmit a lot of raw data for calculations which are then done on the platform side.
Yeah, maybe I can add something to this important point from Wolfgang. So I think that's very interesting also for our branch in future. That we in automation we need to know how many computing power we need right in the application, right on site of the application, and how many computing power we are able to transmit to the internet and do there some calculations, for example. And that is something which we learned from technologies like IO-Link, and what we get from IO-Link technologies, and what we now are able to transfer also to these IoT topics.
Okay, now we were talking about glass. We're talking about the winter project, smart winter project. There are other use cases, for example, the wood pellets. And what else could you imagine where sensors could be used for cities and making cities smarter?
Well, if I may answer that, after we started in Heidelberg, we had, of course, during these 2.5 years, different requests from other cities, specifically in the area of North Rhine-Westphalen, where a lot of projects running where we are, for instance, looking for clothes, for used clothes containers, or a paper. So all the material which is typically for recycling purposes are a clear application for our sensor. In the LoRaWAN, very typical applications are all the metering, like water and heating, but this is not our field. We are not delivering sensors for that, but they're all using the LoRaWAN, and that's why LoRaWAN is spreading quite well over the cities. But our technology momentarily is concentrated on ultrasonic. And we are also looking into the direction of measuring water levels and things like this. So the applications are really growing and growing.
And well, the good thing is that the Pepperl+Fuchs family is offering a huge product portfolio of ultrasonic sensors, and they don't have to be autonomous. They can have a socket just to get some voltage.
Yes, Oliver, you're totally right. I want to come back to the presentation before about the 18GS sensor, which was presented by Till. And here we can see that our IO-Link sensors in general have a lot more data than we just expect. We have the process value, which is in this case a measurement value, but there is some more data which the user can use, or which makes the sensor for the user really interesting. And when I start with the parameter data, so for example, for this ultrasonic sensor, the 18GS, we make the user, or we give the user the possibility to adjust the sound beam width, or we make it possible to adjust something like a window parameterization or a foreground suppression. And there are a lot more parameters which we offer to the customer to adjust our sensors. And then there's a third point I want to mention. These are the condition data. Condition data, they offer us kind of diagnosis and in detail what is meant here. For example, temperature. Temperature information about the sensor. How is the sensor feeling? Is it too cold? Is it too hot? Or things like an operating hour value within the sensor. So how long is the sensor already working? And these are all information the user can use for doing, for example, predictive maintenance. And there we have then the possibility to go inside Industry 4.0 applications.
And maybe the bottom line is just wow, because when we think back of the first proximity switch in 1958, you just mentioned at the beginning of our panel discussions, the possibilities today are huge. So thanks a lot to you to Sonja, to Michael, Dominik, and Wolfgang. And of course, thanks to you, dear guests. It was a pleasure hosting this event with Pepperl+Fuchs, this online summit, and I hope you'll join us next time. And once again, if you have any questions, whatever it is, just use our contact form and get in touch with the Pepperl+Fuchs company. Have a great day. Take care. Bye-bye.